So, my name is Oren Einim. I'm here to talk about highly available and scalable solution with RavenDB. And this is the solution, this is the state that we used to be in. We had a few users, you can see that they are happy, and then stuff happened and they were gone. They were gone and they were replaced by this mob. Tons and tons of users that suddenly wanted to use my application, and I'm pretty sure that I didn't allow that. I didn't allow that, I didn't allow for that. The problem with talking about scale is that this is a very hard to put down metric. We can talk about scaling in the number of users, we can talk about scaling in the number of operations, scale in the size of the data. It's really hard to give a hard and fast definition. One of the interesting things is scale of what? Not all operations are created equal. For example, if I'm talking about something like an online shop, you have many more people browsing your shop than actually purchasing something. So the scaling requirement for the shopping cart versus the product catalog are completely different. One of the most frustrating things in my perspective is that people do a very bad job in actually saying, okay, we need a scalable system. And when you start talking about them, they tell me things like, oh, we want it to be like Google. And then they refuse to give me the Google budget. So typically, I try to say something like, okay, I want to have a few sets of requests. I'm going to define that type 1 request should be X operations per second per node. That's a definition that has number in it, and I can stand behind. Now, as I said, that really depends on what type of operation do we have. Read mostly requests are very easy to scale out by just spreading them over multiple nodes. Then again, if you can support 20 requests per second per node, that means that if you have large number of users, that's going to take a lot of time to run. Not just a lot of time to run, just lots of servers. Servers cost money. By the way, anyone has any idea what is the cost of a server today? A server in AWS, an M4 large, would cost you about $1,000 per year. In other words, if the question is, do I need another server? The answer is, if you have a meeting about it, it's too expensive. Just get the server. Literally, if you have a meeting with 8 people to discuss, do we need a new server? And unfortunately, I've been in those meetings. And then at some point, I just here is the total billable hours for everyone in this meeting. That's enough for 6 servers. And let's just buy them and let me go on with my work. So let's talk about actual practice. First of all, we're going to talk about RavenDB. RavenDB is a document database. This is what this looks like. Documents inside RavenDB are stored as JSON. This has a lot of nice advantages. One of them is that we don't have to spread the data among multiple tables. It means that we can support complex data structures, and everyone is happy. One of the things that we try very hard to do with RavenDB is to make sure that it's highly performant. What is the relationship between performance and scaling? Anyone? It's usually inverse. The more scale you can support, the slower you become, up to a certain point. Actually, the faster you are on a single node, the harder it is for you to move to multiple nodes. That is because a lot of the time when you talk about a single node, there's a tremendous number of optimization that you can apply that just doesn't work when you have multiple nodes. So let's talk about RavenDB just a bit. This is how we do some writes to RavenDB. If you're used to an Hibernate entity framework, this should be very similar. If you use any type of ORM, again, pretty much the same thing. The core features of RavenDB is that it's transactional. That means real transaction in the sense that if you pull the plug from the machine, then the data is safe, and you have transaction that is either all the way in or not at all. It's freely queryable, and freely queryable means that you can write any query that you want, and the server will just handle that. That's actually bring an interesting problem. How many of you are familiar with the horrible pit of success that we send clients into? What do I mean by that? Anyone here ever worked on an application that when a small user went in, they have maybe 5, 10, 20 orders, the application is snappy and easy and fun to use. And when you have the big customer, the customer that has thousands of orders, then the system is slow. And this is typically happening because the developer did things like select stuff from orders where customer ID equal X, and failed to consider that the value of the number of orders for a big customer may be in the hundreds of thousands or more. And then you get into certain interesting things like 17,000 database queries per page view for a particular customer. That's my personal best so far. I'm pretty sure that there are other people who have more. I worked on that particular problem for a few days and managed to get it to 72 queries per page, and I call it quit because I couldn't stand it. But freely queryable, so we have queries like that. What's the problem with a freely queryable system? If I'm going to a database just start issuing queries, what's going to happen? Let's see. So by the way, this is the Northwind database. If you're not familiar with it, this has orders and products and stuff like that. And what I'm going to do now, I'm going to query products, and name is Chai. And you can see here that it uses an index called product name to answer that. Now, if I want to say, notice that it took slightly longer to answer this question. And the index that it uses is auto products by supplier. I run this again, somewhat faster. Let's try category. What's happening here? What's happened is that we started issuing queries, and there was no index to match that query. What's going to happen in a relational database when you do something like that? Table scan. How do we also call table scans? 3 a.m. wake-up calls. So just to give you some background, my company started as a database performance consulting company. That means that the 3 a.m. wake-up call, you would go up, fix that somehow, and then call me. And then I would come and say, okay, and then I would take the template that I have prepared already, check you have unbounded result set, check you have too many page view database queries per page view, check. Here is already prepared a report on how to fix that. And we just make sure that I do a search replace for the company name, and I'm done. And that was a highly profitable and incredibly annoying way to make money. Mostly because I would keep, basically it was going into the sewer every single day and smelling different type of, and one of the things that eventually this came up, this is, okay, it's not possible that everyone who calls me is an idiot, okay? So there must be something in the environment that caused them to fall into the same set of traps all the time. And that's how RavenDB was born. RavenDB was born because I was sick of seeing the same errors over and over again. So what we did was something very simple. We sat down and designed a database that was safe by default. That means that all of the issues that we are typically seeing in standard applications For example, unbounded result set. Let's not allow unbounded result sets. We have a whole class of problems that just went away. Now we have people who complain about, oh wait, my data grew so large and now I can't see some of the data. Yes, that's a feature. That means that you can come to the office on Monday and fix that instead of staying the weekend in trying to figure out how to re-architect your entire system on the fly at 3 a.m. So one of the things that was really annoying for us was the issue of indexes. People make queries, sometimes really strange queries on their systems, and then they expect the database to answer them. And honestly, it's not fair to the poor database. You have a horrible schema, you have a horrible query, and you expect it to give you answers quickly, efficiently, and with a lot of users queuing up to make a lot of requests. With RavenDB, we says, okay, you know what? There is no such thing as a query that doesn't have an index. A query in RavenDB goes to the query optimizer. The query optimizer then selects the appropriate index to use. What happens if there is no appropriate index to use? Well, at this point, we have to fall back into doing a table scan. Now, instead of doing a table scan, it means that instead of doing a table scan, read all the data, let's read all the data and create an index for you. And this is exactly what happened now. You can see that this is an index definition. It says, over all of the products, I want you to index the category and the supplier fields, and this is how you get them, and that's about it. And notice that if we go and look at the products, notice that we have two automatically created indexes. One of them is product by supplier, one of them is by category and supplier. What happened is that first we query by supplier, and the query optimizer created this index, and then by category. So the query optimizer extended this index with the new information to create this guy. Why is this important? This is important because it means that over time, the query optimizer is able to actually learn what query your application is doing and create the appropriate index. This guy is going to sit here and basically go stale and expire after a while because no one is accessing it. So it's going to be marked as we don't care about you any longer. So that's one way of ensuring high performance. How this relates to scale? It relates to scale because the more operation we can do on a single node, the fewer nodes we can have, the less headache we have to manage. So, the first thing that we want to deal with is called sharding. What is sharding? Sharding is when we have enough information that we can't or don't want to put it on a single node. With the standard recommendation for RavenDB, when you go past 1 terabyte per node, you typically say, okay, let's start considering sharding. Typically, we want to something around 300 to 400 gigabytes per node using RavenDB. Now, what does it mean to split the data? What's the problem with just splitting the data? Consistency. So one of the problems is if I have orders on one node and customer on the other node, it's really hard for me to actually ensure that the data on both nodes is consistent. One way of doing that would be to use distributed transactions. Anyone use distributed transaction in production? Yeah? You're ashamed to admit that? Yeah. Anyone had ever run distributed transaction in production? Ever? Anyone here did not regret it? Yeah. What's the problem with distributed transactions? It assumes that all parties to the transaction are going to be up and happy to complete the transaction throughout the life of the transaction, which is evidently not true in the real world. So we don't have a good way of actually ensuring consistency of transactions in a distributed fashion. That is actually a lie. There is a whole series of research paper and practical implementation on these, Paxos and Raft being the most obvious of them. Unfortunately, they tend to be really complex to handle and not something that you would typically use. Most distributed database systems use something like that, but I don't want to go into that. Even so, it's complex with data distribution. So with RavenDB, we have the concept of data-driven sharding to try to ensure data locality and intelligent behavior. That's a lot of buzzwords that are really interesting, but let me show you code so you can understand what's going on. So is the font big enough for the guys in the end? Let's just increase this. So we define a sharding strategy. In this case, by the way, sharding sometimes is used for splitting a lot of data. In many cases, it's used in the sense of geo-sharding. I have information that must reside in the EU. I have information that must reside in the States. Or maybe just, I want to put information close to where the user are actually going to use that. So I define a document store with the database EU and another document store with database US. And then I'm defining the data-driven rules for sharding. So in this case, without understanding what the code is doing, what is it saying? Can someone tell me? These 2 lines of code. This is saying that we want to shard all of the companies by the region they belong to and the orders by the company they belong to. Basically, this means that all of the EU orders, all of the EU companies should reside in the EU, all of the US orders should reside in the US. Orders should reside in the shard for their company. And I will just do this. So as you can see, I'm going to create an EU company, and then I'm going to create an order for that company. And now we're going to go here. We're going to the EU database. And you can see that I have orders 33 and companies 33. The companies 1 and orders 1 is from the previous run. And now I'm going to change that to run on the US. And run this again. And the information is now going to reside in this database. Everyone sees the code? Everyone sees that? So based on the region of the company, we decide where the document is going to reside. Based on the company of the order, we decide where the order is going to reside. So far, pretty simple and pretty easy to understand, right? What's going to happen when we start making queries? Remember that I said that this is an intelligent solution. So let's take a company name, company ID. Okay, let's run this and see what's going on. We got some results, and now you can see something really interesting. Do you see this guy? Here is the query that we asked, company US, company 65, and this was issued only to the US node. Why was that? Why did we only ask the US node? Yeah. We know it's sharded. We know we can look, okay, we know that we shard companies by the region. I know that I put it in the document key to make it easy to actually make those kind of decisions. So I can just go there. I don't need to do I don't need to go and ask all of the servers. Now, RavenDB has the concept of MapReduce. In this case, what I have here is go over all of the orders, go over all of the lines, and for each product, output a count of 1 in the map. And then in here, let's group things by the product and get a summary of the count. Now we have orders that reside on both servers. We have orders that reside on the EU server and orders that reside on the US server. Let's see what happens when we issue a query on that. Okay? Notice that from the point of view of our code, this is what we do. Okay? Issue product on sales, on product sales. And now we get product 1 has 3 cells to it. If we go here to the EU and look at the index, it has 2 cells. If we look at the US index, then we have 1 cell. Effectively, what happened is that we went to both nodes and got the reduced result and then re-reduced them again to get the final result that is valid across the entire cluster. That's all really nice and well, and this is a feature that has existed in RavenDB for the past 5 years or so. It's a nice feature, but I don't like it very much. Mostly because there are things that still need to be handled by an administrator. For example, if you add a new node and you want to start moving data around, that's possible, and there are solutions to do so, but it's not as convenient as possible. In the 4 version of RavenDB, we'll probably do a whole lot of work around that, but that's beside the point. So that's one way of handling scaling. Another way of handling scaling is using replication. What does it mean to have replication? Same data on multiple servers. So I happen to prepare it in advance, a database. We call it Northwind. And you know what? I will And now this database actually replicates to Northwind 2 on the same machine and to a live test instance available on the cloud. Actually, this is this instance. You can go to live-test.ravendb.net right now and see this database. Now, let's see what it means to have a replicated instance. And I now created a user called Matt. And now I'm going to go here. And here we have a user called Matt that was created on the remote instance. Yes, 1 second. By the way, the hotel network is horrible, so that's why we see this high latency. But this is good. It will allow me to show you some really cool stuff. Now, what's the point of having replication? Anyone? Sorry? Not to lose data. Okay. So this is the code that I have. I think you will agree that this is, you know what, let me just even make this simpler. Let's remove the setup code, and everything can fit in a single screen. Okay. So this is my code. What do you notice about this code? What is it doing? We have a document store. This is the connection. This is all of the details about the connection. We open a session. Then we query the database for a particular company, and we write it to the console. Anyone is shocked about this code? There is something unfamiliar or strange about this? No? Great. So notice first time it's slightly longer because we need to establish a connection to the server, and then it's pretty easy. Now, we have the data on multiple nodes. We saw that here, that we have Matt. We can see that here, when we go to node win 2, and we can see that we have Matt as well. In this case, the demo that we use is on companies, and you can see this here. Now, what's the point of having an application? To have the data on multiple nodes, right? Well, what happens when a node goes down? What are you going to do then? I'm going to hit enter. My client is going to hit the database. The database is going to say, oh, this database has been disabled. You can't use it. Ah, that's interesting. What happened? It went to the next one. Now, let's kill it and run it again. Notice that I don't have the next one in here. What's going on? The RavenDB knows when the next one, but oh, you know what? Okay, you're correct. Let's kill this one. Let's kill RavenDB. Now it will properly fail for me. Huh. Okay. This is actually going to take about 6 or 7 more seconds. Okay. Where is it getting it now? We shut down the server. We restart the client. One of the things that RavenDB is trying to do is to be robust. And this is what happened. We have the replication that take care of distributing data among all of the members in the cluster. When a client connects, it's connected to the primary node in the cluster. The primary node in the cluster is just the node where the clients connect to. There is no special distinction there. And now, I'm going to go here, re-enable this guy, and I'm back reading from the right database. Now, let's go to status. This will take a while, but it will allow me to explain. So we send to, okay, great. So now we can actually see the actual topology. First time the client connected, it connected to this guy. And then it asked it, okay, give me your topology. And then it cached that locally. Cached that locally on disk. So when this one is down, even after a client restart, we know what the topology is. It updates all the time whenever there is a change. So typically within 5 or 10 minutes of a topology change, all of the clients know about it. But the basic idea is that once the client has connected once to the server, then it knows about the entire topology. Now, notice something very interesting about this. What is the topology that we have here? We have a master server, we have a slave server, and we have another slave server. Okay? So all of the changes that happen on one node will be reflected on the 2 other nodes, but not vice versa. I can't make the cloud machine talk to my machine because of firewall rules, but I can make it happen the other way around. So I'm going to go to the replication. Go to node win 2 and make this into a master system. And now I'm going to go there, and now we will see that this is now changed to be a master system. What does it mean in master system? It means that I can do the following. I'm going to take this down. And in here, I'm going to change this to be so the node is now down. I'm restarting this node. And go to companies 1, and we have it. Replication in RavenDB is based on the shared nothing principle. The idea here is each node is absolutely independent of one another. We don't care that they are up, we don't care that they are down. All we care is that I'm up, and whenever I'm up, I'm going to start talking to people. It's happened in an async background way. Typically, it's happened immediately, but under certain load condition, it can queue up a bit. And as you've seen, there is automatic failure and recovery. One of the things that is possible for us to do is to say, you know what? One way of scaling out would be, okay, we already have 3-node cluster for availability. Let's make use of this 3-node cluster for scalability by load balancing all of the requests among all of the nodes. So we can do a round robin load balancing. There is SLA based load balancing, so we always go to the least busy server and all sorts of stuff like that, but that's the idea. This behavior is controlled by a client-side policy. This is so clients can define things like, okay, the server may be very fast, but I have to go through a busy router. If I go through a busy router, what does it mean? It means that the server thinks that it is replying very fast. The client sees that the reply back violates the SLA. So it can decide, okay, I'm talking to this server and it's too slow for me. I'm going to switch over to a secondary server. And that's where you have balanced actual load on the system, not only on your database, but also on your entire infrastructure. Now, one thing that I didn't mention is what's going to happen, what is the problem with async background replication. And let's see what's going to happen now. I'm going to shut down Northwind. And in Northwind 2, I'm going to go here and add Destin F2. Now this is shut down. And this is up. And because this is up, no one can tell me that this has been updated. What's going to happen now when I'm going to bring this node up again? We have a problem because we have 2 effectively concurrent modifications to the same document that doesn't have the same history. So now when I'm going to look at this guy, I actually have a conflict. The UI does a good job of making it look like this is a source control conflict. Yeah. Now resolve the conflict. And I can go here and this is resolved. I could actually specify the behavior here, whatever resolved to local, remote, latest, blah, blah, blah. Doesn't actually matter. This is just tip of the iceberg in terms of replication and scale out in that regard. The idea here is that we can very rapidly increase the number of processing power that we have in the cluster, but at the same time maintaining the complexity of the work. The usual way that you work with the RavenDB replication cluster is that you designate a single primary instance. All of the writes happen there. So things like optimistic concurrency, things like a transaction that span multiple documents, all of them are supported very easily out of the box. You do have to be aware that in certain failure conditions you may have conflicts. You can either resolve them automatically via the configuration or register something called a conflict resolver on the client side that get all of the version and resolve them for you. Questions so far? Okay. Another way of having higher scalability or higher performance in general is to do something very interesting, to do less. Now, Typically, we see user designated certain nodes for certain actions. For example, this is the user authentication node. All of the user data is on it. And this has 3 separate nodes dedicated to that because this is super important for us. In RavenDB 3.5, we have the options of doing replication on a collection by collection basis. So all of the users are here and replicate all of the other nodes, and that's it. And this node is for orders. Orders would have, 5 different servers sharded with a replication factor of 2, and for the same reason. But another way of doing that is to say, okay, let's do something else. Let's move the data for certain needs outside of RavenDB entirely. Typically, that happens when you have things like OLAP cubes, existing reports, or a system that already exists. So, second. Okay. So here we have a nice database. And we have a nice table. And we have some data. Can anyone see the data? It's not particularly impressive set of data. Now, let's go into RavenDB and create a user. Let's copy user because copy paste is better. And he lives in. And let's run it again. And something interesting happened. What just happened? Do you see this guy? Let's do something. And we have him here again. What did we just observe? We observed that we modify data inside RavenDB, and this data appears to have magically appeared inside a SQL server. What's the purpose of this feature? The idea here is that RavenDB is an OLTP database. What does it mean that it is an OLTP database? It means that it's good for transactions. If you want to start slicing and dicing your data, if you want someone to start doing pivoting and all sorts of stuff, there are existing tools for that. RavenDB is not meant to do so. So, okay. That was another failure condition that we need to handle. So RavenDB has something called SQL replication. And we specify a collection string. We say that all of the users' collections go to users table with that. And now we replicate it in here. This is basically just a JavaScript script that specify the transformation from RavenDB documents into various tables. Another way of doing that would be to, now in this case we have only a single table. We can also have more complex stuff, as you can see here with orders and order lines and stuff like that. And the idea here is that typically a single RavenDB document is represented by many rows in a relational database. So this gives you the freedom to write to RavenDB, do all of the work, and then do all of the usual reporting in the standard relational pattern. This also helps a lot to your system performance scalability because it means that the OLTP database, the one that actually serves pages to the web applications to the user, is not currently being busy by running the end of quarter report. Questions?
Do you have a feature that does the opposite?
No. The reason why not is that this actually requires a lot of support from the database. You can sort of do that if you write a lot of triggers, but my condolences if you do. Uh, yeah, just to give you some ideas of the complexity of these features, what happens if we shut down SQL for a particular period of time and then restart it? This feature handles that and will send all of the updated values from the timeout period. But what happens if this is not a database inaccessible? What happens if there is certain documents that have a constraint violation in SQL? And blah, 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 blah. It gets to really ridiculous levels at certain points, the amount of error handlings that we have and error handlings for the error handling and all sorts of stuff like that. But yeah, I don't think that you can do an efficient way of handling that inside a database without actually being really aware of the kind of changes that you have, the kind of internal behavior in the database. This, for example, relies on an internal feature of RavenDB called an E tag that is always sequential. So we only need to remember what is the last successfully replicated E tag. By the way, this applies both to RavenDB replication, RavenDB to SQL replication. Because of that, we're able to handle failures very nicely. More questions? Okay. I started this discussion saying that I made my money at a certain point by fixing database performance problems. And that RavenDB was all about, let's not get into the same mess again and again and again. So what common performance problems are you familiar with talking to databases? Think about it. Yeah.
Extremely long-running queries.
Long-running queries. Okay. So typically with RavenDB, that doesn't happen for several reasons. Why would you have a query that runs for a long time? Typically that happens because A, you're running a query that gets a lot of information. With RavenDB, we tend to have a hard limit on that. If you try to get more than 1,000 results with RavenDB, we're going to say, that's nice, please don't do that. So let me show you what. Can anyone see the code? So let's assume that they have 100,000 products in my database. So I'm calling two lists on them. The way that it would work on a relational database, the database would start sending the data, you would start batching all of the information inside your memory, you get all of the 100,000 items, and then you give it to the user who only takes the first 5. So with RavenDB, after seeing that issue way too many times, I said, okay, enough. We have a hard limit of 1,024 items per query. If you want more, we just ignore you. The reason that we will just ignore you and not accept an explicit limit is that people do that to fix a RavenDB bug. So with RavenDB, we have two ways of accessing the database. One of them is the standard OLTP. I need to show a web page with some information. And the other way is called a stream. You have a query, it does something, and then you stream that query. And with streaming, you don't have a limit of how many items you see. Another reason that you have long-running queries is that the queries are expensive. Now, what will make a query expensive? Yeah.
Non-existing indexes?
So, one second, non-existing indexes and?
If you're looking for a field that doesn't actually exist.
That would just create an error.
Joins.
Sorry?
Joins.
Joins. No joins with RavenDB, that's easy. No non-index query with RavenDB, so that's easy. What else is complex?
Aggregation.
Aggregation. Okay, let's wait for that. What's more? Anyone ever see the query that made your eyes bleed because it did 17 different things and had more business logic than the enterprise? So one of the things that we don't do with RavenDB is computation. We don't allow computation during query. That leads to interesting problems. If we don't have computation in query, that means that it's really hard for us to answer queries. Okay, give me all of the orders where the total value is higher than X, because there is no field called total value. What we have instead is all of the line items and their own value. In order to handle that, we use this. This is a static index that you predefine ahead of time, and it basically tells RavenDB, okay, let's index that, and let's do the computation during indexing time. Why is this important that this operation happen in indexing time? A, how often do you index? Whenever data changes. How often do you query? A lot more than the data changes. Second, what does it tell this? What happened to this guy? It means that instead of having to go over all of the data set, load the document, compute it, check yes, no, and then most of the time throw it away, I can just do an O log n search inside a sorted data structure and give you the result immediately. We typically, in conversion from SQL Server to RavenDB, we typically see 2 orders of magnitude improvement. Not just because RavenDB is faster, but because it makes sure that you don't have the same stupid traps all over. The other reason that things are slow is for aggregation. Now, let's see how we handle aggregation with RavenDB. There are actually 2 ways. The easy way is using MapReduce. How many of you are familiar with the term MapReduce? How many of you are scared of that? How many of you don't want to admit that? So one of the problems with MapReduce is that it sounds like a big, very fancy thing. MapReduce is actually a very fancy name for a group by. How many of you are afraid of a group by? You had experience with production, I see. So with MapReduce with RavenDB, we split the aggregation operation into 2 steps. The map basically goes over all of the orders, go over all of the lines, and then get me the total based on that. And then in the reduce, let's go and group things by the product and sum the count and the total. Anyone does not understand this? Great. So now let's see what happened when we query on that. When we query on that, what happened is that this is actually really slow now. Let me try it again. Okay. That's better. What happened is that the timing that is reported here is reported on the server-side timing, and it was cached. So also the original time was cached. So typically, I would expect a query on MapReduce index to complete within 10 milliseconds or so. The faster, the better. How can it do that? It can do that because it isn't actually doing any sort of computation. Let's look here. And okay. What you can see here is that we have order 141, and it has 3 different products in this order. The map extracts this data for every product, and then the reduce combine all of them together for the same product. When we query, what are we querying? We're querying the data that is in here. So let's assume that they have 100 million orders with 10 items, 10 line items in each. That comes to about a billion line items. And now I want to say something like, okay, how many items have we sold from product 52? And if I'm using a relational database, what I would have to do, I would have to go and count all of them. Hopefully, I have an index on that. If not, then I have to they have to go through all 1 billion of them. But in practice, what I'm doing here, I'm going to say, okay, let's go to the end. I already computed all of this work. I can just give you my pre-computed result. Now, the problem is that what happened when we update something? What happened is that, again, what I would have to do is I update orders one for one, then I have to update this, I have to update this, and then I'm done. The actual behavior of the system is a lot more complex, but that's the general, that's blah, 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 blah. Sorry, I lost the ability to speak for a moment. That's the general way it behaves. That's the conceptual way it behaves. When you modify something, we get the map results, and then we just re-reduce it with the final result, and we are done. Even on very large data sets, reduce can keep up with the ingest rate, and queries are done on the pre-computed, already computed data. So they're insanely fast, even for really complex queries that takes hours to run on a relational database.
Does that not make the inserts or updates slower?
No, because this actually happens in the background. The reason that it happens in the background is that we don't want to force you to slow down writes. By the way, with RavenDB in general, indexes are running in the background, but that's a different issue. Questions? Either did a really good job or really bad job. Yes?
What is the memory impact on RavenDB compared to a normal SQL server? It seems like you use more memory. Or,
Depending on the actual usage, we tend to take less memory. We tend to take less memory than SQL for most operations because a lot of the things that we are doing are already working on memory map files. So it's hard for me to give you an exact answer. The working set tend to be smaller. The actual virtual address space is we map the entire database into memory. Questions going once? Guys, laugh all you want. Going once, going twice, going twice is a surefire way of saving the. Any question? Yes, no, no, no. Okay, but all right. I have a question. Okay, questions going once? I have a sticker if you ask a question. What? Yeah. You see it works.
Yeah, of course. Schema migration. That's a typical problem.
Also take some. The schema migration. Typically not a problem because we are generally schemaless. You can also do something like this and just write script that modify this in some way. The canonical example is you have a first name, last name, you want just a name. Those sort of things. Write the script, run it, and that's it. Okay, guys, I think I ran out of time. If you have any further questions, I'm at the booth down there somewhere. Thank you very much.